discussion on integration, and specifically we're going to begin by proving a few more conditions under which one may guarantee integrability of functions. Alright, so the first of these is the theorem that's on the screen, which is that you have a function which is integrable over one interval, say a comma c, and also on the interval c comma b. In that case, it is also integrable on the union of these two intervals a comma b, where the integral from a to b is in fact the integral from a to c plus the integral from c to b. Right? Again, this is something that we have used on umpteen occasions, I'm sure. All we are doing is giving a rigorous argument for this, right? And the central idea behind this proof is going to be simply that you can think of partitions between on the set AB, on the interval AB, to be a union of partitions over AC and partitions over CB, right? So by taking the union of these partitions, you can get partitions on the bigger set A comma B, and which is what we will use, right? In addition, of course, to the integrability on the subintervals AC and CB. Okay, so proof. Given epsilon greater than 0, okay, there exist partitions P1 is on AC and P2 on CB, such that, well, the upper sum of f on P1 is at most the integral from A to C plus epsilon by 2. Right? This is always possible because of the integrability over the interval A to C. Right? Plus, additionally, u of f comma P2 must be less than integral from C to Bf plus epsilon by 2. Right? In both of these cases, integrability ensures that the value of the integral over the corresponding interval is also equal to the infimum of all upper sums across partitions. So if I give myself an epsilon by 2 fudge on top of the infimum, there must exist a partition whose upper sum is in fact less than that. Right? So now we will use the fact that P, which is the union of P1 and P2, is a partition on AB. Right? So now let us try and see what we can say about UFP. Okay? Now, UFP involves a summation over all the subintervals which are contained in both P1 and P2. Right? And in each subinterval, basically the corresponding supremum times the width of the subinterval is already captured in UFP1 and UFP2. Right? And since these intervals are disjoint, the subintervals are disjoint except for the endpoints, U of Fp is in fact exactly equal to U of Fp1 plus U of Fp2. Right? And we already have bounds on UFP1 and UFP2, so therefore UFP is at most integral from A to CF plus integral from C to BF plus epsilon. Right? Now the upper Darboux integral of the function f over the entire interval AB is this infimum of UFP over all P. Right? So that in turn implies that UFP, now here I should clarify that this is over AB. Right? This UFP is therefore less than equal to sorry, I got this wrong. What I mean to say is UF, right, over AB. Okay, this is the infimum of UFP over all P. This is going to be less than equal to UFP, which is therefore also going to be less than equal to the upper bound, integral A to CF plus integral C to BF plus epsilon. Right? and this is in turn true for all positive epsilon. So this holds for all epsilon greater than 0, which in turn implies that u of f, once again over ab as I mentioned before, is less than or equal to integral a to c f plus integral c to b f. Right? So UFP is less than equal to integral from a to c plus integral from c to b. Right? And you can just easily repeat the above steps to analogously show that L of f must be greater than or equal to the same thing. Similarly, can show that L of f is in fact greater than or equal to the integral from a to c of f plus the integral from c to b. Right? And patch these two inequalities together, and you see that u of f is equal to L of f is equal to integral from a to c plus integral from c to b. Right? So that in one shot proves two things: that the function is integrable over the interval ab, and in addition the value of the integral is given by the sum of the values of the integral over ac and cb. Alright, so that's the first result. The second result we are going to prove is about the integrability of piecewise monotone and piecewise continuous functions. We have already talked about integrability of monotone and continuous functions. Now we are going to talk about piecewise monotone, piecewise continuous functions. So before I state the result, I need to tell you formally what I mean by piecewise monotonic and piecewise continuous functions. Right? So let's start with the definition of that. So f, the function f defined on the interval ab is piecewise monotonic right? If essentially, one can come up with a partition such that in each subinterval of the partition, the function is monotone, right? So that's exactly what we're going to write. If there exists a partition P, let's say P equals A0 equals T0, T1 all the way up to Tn, which is equal to B, such that F is monotone on each of the open subintervals tk minus 1 through tk for all k 1 less than equal to k less than equal to k. Right? So essentially, it's piecewise monotonic if there is a partition such that over each subinterval of the partition, the function is essentially going to be monotone, or at least on all of the open subsets, open subintervals of the partition, the function should be monotone, right? So in particular, it's okay for the function to alternate between being increasing and decreasing, right? So over one subinterval it could be increasing, over the next it could be increasing, then decreasing again, and so on, right? So for example, a sinusoidal function would count as being piecewise monotonic, right, by this definition. The next definition is going to be for piecewise continuous. The function f, which is defined once again over AB, is piecewise continuous if once again there exists partition P with the same notation, right? So I'm not going to rewrite the notation for the partition. There exists a partition P such that f is uniformly continuous. Now this is crucial. It's uniformly continuous on each open subinterval tk minus 1 through tk for all k between 1 and n. Okay, so piecewise continuity implies that you have to have uniform continuity on all the open subintervals that make up the partition. Okay, so that's the definition of piecewise continuity. If you so the main result to prove, of course, is that if a function is either piecewise monotonic or piecewise continuous, the function is in fact integrable. If f is piecewise, let's maybe say continuous first. If it's piecewise continuous or piecewise monotonic and bounded, on AB, then f is integrable. Okay, now note that in the hypothesis there are two possibilities for which we are saying integrability is guaranteed. One where the function is piecewise continuous, or it is piecewise monotonic and additionally bounded. Okay, so in addition to piecewise monotonicity, we require boundedness. One thing to remind you is that our definition of the Riemann or Darboux integral is currently well defined only for bounded functions, right? Once you have an unbounded function, the supremums and infimums involved in the upper and lower sums can become plus or minus infinity, right? In which case the sums are not well defined. So we'll talk about improper integrals later on. But at this point, our definitions only apply to bounded functions. It turns out that piecewise continuity implies boundedness. So we didn't need to separately enforce boundedness because piecewise continuity implies boundedness. However, piecewise monotonicity does not, right? So in addition to piecewise monotonicity, one needs to assume boundedness to be able to show that the function is integrable. All right. So proof. Now, in light of the previous result that we showed, right, that if you have integrability from A to C and then from C to B, then you also have integrability from A to B. An induction argument on top of that will tell you that all you really need to do is show that the function f is integrable over each closed subinterval in my partition. So it suffices to show that f is integrable over the closed subintervals tk minus 1 through tk for all 1 less than equal to k less than equal to n. This is using the previous theorem, right? So all I have to do is show this, right? Given that in each of the corresponding open subintervals you have either monotonicity or you have uniform continuity, right, by definition, right? So now let's go about arguing this. Now, if f is piecewise continuous, then I claim the following: its restriction on, let's say, tk minus 1 through tk. Okay, look at this restriction on the kth open subinterval of the partition. Okay, the restriction of f to this admits an extension, shall we say a continuous extension fk over the closed interval tk minus 1 through tk. Okay, So if I restrict myself to the definition of the function over the open subinterval tk minus 1 through tk, because it is in fact uniformly continuous over this open subinterval, there is a continuous extension of the function which actually covers the endpoints, and I'm just going to refer to that extension as fk. Right? This is something we had already proved, that a function is uniformly continuous over an open interval if and only if there is an extension of the function which is continuous over the corresponding closed intervals. In other words, I can define the values at tk minus 1 and tk such that over the corresponding closed interval, the definition now becomes continuous, the definition of the function. Okay, so I can do this for piecewise continuity, and so therefore this fk is clearly going to be integrable on the closed interval tk minus 1 through tk. So that covers the case of piecewise continuous. If f is, well, we have assumed both boundedness and piecewise monotone. So if you have both of these, you can also do the same thing with f. So its restriction on the open interval tk minus 1 through tk also admits a monotone extension fk over tk minus 1 tk, right? So if you are both bounded as well as monotone over an open interval tk minus 1 through tk, I can define an extension of the function which is monotone over the corresponding closed interval, right? Why can I do this? The simple way of doing this is that you pick the value at tk to be simply the supremum of the function values over the open interval tk minus 1 through tk, right? Which is a real number because of the boundedness assumption. Similarly, you define the value at tk minus 1 as the infimum. When you define it like this, you are guaranteed that the extension is also going to be monotone over the closed interval tk minus 1 through tk, right? In both of these cases, note that the function fk is integrable over tk minus 1 tk, right? So in the first case it is integrable because fk is continuous over this interval. In the second case it's integrable because it is monotone over this interval, right? Now since fk is integrable over this, my claim, and this is the main step of the proof, is to show that f is therefore integrable over tk minus 1 tk, right? And why is that? And this is, I'm going to leave the precise justification of this to you as an exercise. The main idea here is that f and fk differ only at most at 2 points. At most. Right? So essentially you should be able to argue that if I have an integrable function, fk in this case, and if I change the value of the function at any finite set of points, in this case 2, the new function, the perturbed function, will continue to be integrable. And in fact, you should, in the same stretch, you should also be able to show that the value of the integral remains unchanged because of this perturbation at some finitely many points. Right? So since fk and f disagree at most at the endpoints tk minus 1 and tk, f remains integrable, and the value of its integral over tk minus 1 through tk is in fact identical to the integral of fk over the same interval. Okay? So having once established that f is integrable over each of these closed subintervals, the previous theorem kicks in and tells you that it's also integrable over the entire interval a through p. Okay? So that's the second of our results for this video. The final result that I want to bring out is the intermediate value theorem for integrals. Okay, so let's take this. This is, as the name suggests, going to be a consequence, a trivial consequence of the standard IVT that we know for continuous functions. If f is a continuous function, on AB, okay, then there exists x between A and B such that f of x is in fact 1 by b minus a times the integral from a to b of the function f. Right? And what is the interpretation of this? The integral from a to b can be thought of as the area of the function between a and b, area under the curve of the function, if you will. Once you divide by b minus a, that right hand side essentially represents the average value of the function over the interval ab. And what we are saying here is that there is at least one point where the function value is in fact matching with the average of the function over the entire interval, right? And this will be true so long, the existence of this point is guaranteed so long as the function is continuous. All right. So the proof is going to be quite quick. So let M define the max of f of x over x in the interval AB. Right? Now we know that for a continuous function, the maximum value is in fact attained. The supremum value is in fact attained, which is why I can call it the maximum value, right? And similarly, let small m be the minimum value of the function over the closed interval AB. Again, this minimum is attained at some point. Okay. Now, if capital M is equal to small m, that means that f is constant. If f is constant, I leave it to you to show that in fact the existence of the point x is in fact trivial. Any point x between the intervals a through b would basically satisfy that condition. Okay, so this case is in fact trivial. So now assume m is greater than m. Okay, now since m is greater than m, note that if you look at m minus f, okay, this is a non-negative and continuous function over the interval ab, right? Similarly, f minus m is also non-negative and continuous. So our non-negative continuous functions on AB both are not identically zero. Right? So what does it mean to say that you have a function that is continuous, non-negative and not identically zero? As we have proved before, this means that the integral of these two functions is guaranteed to be strictly positive. Okay? And then I leave it to you to show that the strict positivity of these two, of the integrals of these two functions, in fact implies that m is going to be strictly less than 1 by b minus a times the integral from a to b f, which is going to be less than this. Right? All you really need to do is use the fact that the integral of m minus f is strictly positive, the integral of f minus m is strictly positive. Patch those two inequalities, and a simple algebra will show you that the claim I have made here is in fact true, right? And now my result follows from the IVT for continuous functions, because we know that capital M is attained at some point, small m is attained at some point, it's a continuous function, so any intermediate value, and we have just said that the average of the function is an intermediate value, must necessarily be attained. So final result follows from IVT. Right? Since f attains values m and m. Right? That completes the argument. Okay, so that is the statement and proof of the intermediate value theorem of integrals. What we will do is stop here, and in the next video we will talk in detail about interchange of limits and integrals.